welcome everyone for a series of quantum space and seminars that Ashoke Sen will be giving us. This is the first of the 3 seminars that he will be giving us. On Monday, as you know, we will also have a public lecture by Ashoke, and his visit is here till Wednesday. So, for the first lecture, over to you, Ashoke.
Okay, thank you. So it's a great pleasure to be back here. So this is the title of the talk, and it's based on 2 papers that I wrote earlier this year. So let me begin by specifying the question that we will try to address. So the point is, many string compactifications have moduli fields. So moduli fields by definition are scalars which have no potential. Okay, so there are massless scalars and there is no potential. So in principle, they can take any value. And any value basically means any value at asymptotic infinity. In the interior, of course, you can have various configurations, but the scalars can be non-trivial. So the examples of such scalars are, one is a dilaton, right? A string theory in 10 dimensions have this dilaton field, whose value essentially sets the string coupling constant. Once you compactify string theory, you can also have moduli of compact spaces, right? The shape and size of the compact spaces, etc. Right? For example, if you compactify a 6-dimensional torus, then the metric on that 6-dimensional torus will be part of the moduli of the theory. And as I said, these moduli can take arbitrary values at infinity. And the question that we will try to address is whether these different asymptotic values of moduli, whether they should be thought of as different theories or different states of the same theory. Now, this looks like a somewhat philosophical question. So, to answer this, you have to first fix a criteria. Okay, I will first fix a criteria to determine this, the answer to this question. And once you fix the criteria, you have to stick to it. Okay, and with that, there should be a definite answer. Okay, whether the 2 different asymptotic values of moduli correspond to different theories or the same theory. So here is the criterion that we'll be using. Okay, so let's suppose that A and B denote 2 different asymptotic values of the moduli. Okay, so for example, in the 10-dimensional string theory, these could be 2 different values of the coupling constant. And so corresponding to A and B, there will be 2 apparently different theories, one where the asymptotic moduli correspond to A, the other one where asymptotic moduli correspond to B. And here is a replication. So we'll say that B will be a state of A. If any experiment that we can perform in B can also be performed in A. Okay, which means any measurement that we can perform in B, we should be able to perform in A. Right? If this is the case, then we will declare that B is a state of A. Right? This is not an independent theory, but just part of the original theory that is described by A. Okay. And here you also will have to specify what you mean by the experiment. So, like real experiments, you have to allow in an experiment a non-zero error. Okay, it could be arbitrarily small. Okay, but error should be non-zero. And we should be able to do the experiment with arbitrarily large but finite resources. So more specifically, you first decide how much error you can afford to make. Depending on that, you ask for resources, and then you have to be able to perform the experiment with those resources. Right? You cannot ask for infinite resources, and at the same time, you are not trying to do the experiment with arbitrary accuracy. Right? We fix an accuracy, and then we'll have to do the experiment.
So, Ashok, this question can also be asked meaningfully in quantum field theory?
Yeah, it can be. It can be asked meaningfully also in quantum field theory, and I'll be discussing that in a minute. So, for example, the fact that we have finite resources means that we cannot ask an experimentalist to change B to everywhere. Right? We cannot ask them to change the value of the scalar field from B to everywhere because that requires infinite resources. So, to be more practical, right, we consider we can claim that B is a state of A if we can create an arbitrary large region inside A, inside which the modular fields are arbitrarily close to B and other fields are arbitrarily close to 0. Okay, note that we are not demanding that all the other fields are all strictly 0, or that the moduli is strictly that of equal to that of B. But we should be able to bring it to be arbitrary. We fix an error, right, that we are allowed to make, and with that error in mind, we allow we allow the moduli to be not exactly B, but differ from B by a small amount. And similarly, other fields, we don't demand that they are exactly 0, but we allow them to differ by an arbitrarily small amount. Okay, so this is within this framework, we have to decide, okay, whether B is a state of A or not. This is okay so far?
This is asked only in infinite space, right?
In
Infinite
space. Yeah, A is in infinite space, exactly. That's because asymptotically A is it's the value is same. Okay. So here are the results. You will see that in many and probably all cases, if B and A are part of the same modular space, B is a state of A. Okay, if the asymptotic space-time is flat. And if the asymptotic space-time is ADS, then B is not a state of A. Okay, this argument is not foolproof. I'll explain. I mean, basically what you will see is that the argument that we apply here doesn't work here. And there is an independent argument based on ADS TFT that tells us that B shouldn't be a state of A. Okay, but we'll try to remove both on this. Okay. Sorry.
So B is not a state of A. Does it imply that A and B are some different theories?
Yeah, that is our definition, right? These are strongest sense in which B can be a state of A. That if this is okay, the point is, if this is true, that if any experiment that you can measure in B, that you can perform in B can be done in A, right? Then it's clear that B should be thought of as a state of A, right? Now you can try to relax this assumption, right? You can make a milder criteria as to when you will declare B as a state of A, and then the result may change. But if you can satisfy this, right, that any experiment that you can do in a B, you can do in A, then clearly that seems quite natural that you will declare B to be a state of A, right? And then we are not defined theories. Right? B is the same theory as A. And this need not be reversible, right? If B is a state of A, doesn't mean that A should be a state. A will also have to be a state of B. Right? And we will see examples of this, where it is not true. Okay, so there are some arguments against B being a state of A. Okay, this was given by Banks, but I think he based his argument on many earlier results. Okay, or various other people. So let me just give some of these arguments. So first, let's consider a normal quantum field. In normal quantum field theory, if there is a moduli, okay, some scalar field whose expectation value can be arbitrary, then we can achieve B being a state of A by simply creating a large region of size R, okay, so that inside the moduli take the value B. Okay. Now this need not be a solution to the equations of motion. Okay. You think of this as an initial configuration. You prepare the state, okay, in this initial configuration where the fields inside are in B, fields outside are in A. Okay. Notice that we are changing A to B in a finite region, so it can be done with finite amount of resources. And now the point is, once you have created this region, you can put your experimental apparatus inside, do whatever measurement you are to do, and as long as this region R is sufficiently large, right? This, I mean, of course, eventually this will evolve, right? It's going to collapse, but as long as you can finish your experiment before it collapses, you have achieved your goal, right? So that means that any measurement that you could possibly do in B, right, which means put a finite apparatus and you do the experiment with a finite time, you can do also in A by creating this region inside A. Okay, because this is a state of A. This doesn't quite work for gravity, right? So I'll explain what goes on in gravity. So if you can estimate the energy of the domain, right? So there is some energy domain wall, there is some energy density, right, in this domain wall. So let's suppose there is some fixed energy density. So the energy of the domain wall will be given by R to the D minus 2, right? Because that's the area of this surface. If D is a total space-time dimension, then the area of this is R to the D minus 2, right? For D equal to 4, it's R square, right? That's the familiar formula for area. So if we have this much energy, then you can calculate its Schwarzschild radius. In this space-time dimension, the Schwarzschild radius goes as mass to the power 1 over D minus 3. Again, for D equal to 4, this is familiar result. Schwarzschild radius is proportional to the mass. Okay, this is the general formula in D dimension. So now if you use the fact that E grows as R to the D minus 2, we see that the Schwarzschild radius grows as R to the D minus 2 over D minus 3. And this for large R is much larger than R. Okay, so in 4 dimension, this will be like R square. Okay, so the Schwarzschild radius of this configuration will be growing like R square. And that's much larger than the size of this configuration. Okay. And this means that once the effect of gravity is included, this configuration will be inside its own Schwarzschild radius, which is much larger.
So in what limit is much larger than R?
For R larger. Because you want to create this configuration for a large R, right? Because you want to do the experiment, right, with arbitrary accuracy. So for that you need sufficient amount of space and time. Right? So you want to take the large R limit. And in that limit, the Schwarzschild radius becomes larger than the size. Right? So it's inside the event horizon. So you cannot do an experiment here and send back the signal to the asymptotic observer to convey that information. Right? So this measurement you cannot perform.
But there you are assuming that the dimension to quantity in the first like energy relation is coming from G Newtons that
Yeah, this one.
no, where E is proportional to R to the D minus 2.
No, this is like I'm just area. I mean multiplying by the area with the domain orientation.
So field extent. Whatever the landscape, it's that extent.
But also, can you say what's the physics of saying that this thing will collapse? Why would this thing collapse?
Oh, because this is not necessarily a solution to equation of motion, right?
That's right.
So there is a tension of the domain wall. It will try to reduce its energy by collapsing,
Right.
right?
And radiate it out.
Well, whatever happens, right? Once it collapses, then that gives a limited time scale, right? So what I'm saying is, any given experiment, right? You have to do for large amount of time and large amount of space. You fix that first, how much time you need and how much space you need, and then you make a gobble like this, which is larger than that size, right? Then you are guaranteed that you will be able to do an experiment, right? The fact that the apparatus gets destroyed afterwards is of no consequence, right? You can do the experiment and you can transmit the data to asymptotic observer, right? So it's in that sense that you can asymptotic observer already has information about whatever experiment you could do. Okay, so this argument can be this estimate can be made a little better. Okay, let me try to see how that can be done. Okay. And the point is that as if it's a moduli space, if A and B are part of a moduli space, then there need not be a third domain. Okay? We can allow the field to vary continuously from A to B. So you spread out the variation, right? Instead of thinking of this third domain one, you imagine that the domain one is a very fat domain. And in that case, you can easily see that you can gain a factor of R, right? So now how much you can spread, right? You cannot spread more than R. If R is the size of the system, right, then the domain one cannot be larger than R.
Why is that?
Why is that? Because then the size of the system also increases, right?
So if my job is to create D in some region,
Yes.
I could just do that to a very slow variation, which is happening a much larger length.
That is true.
So why can I not? Why?
So then the definition of R itself will change. Imagine that you are varying over a much larger scale, right? Then R is the size of this region, right?
I thought R would be specified in the beginning, like in what region we want to do experiments.
That is true. But in this estimate, okay, that is what you specify. But in this estimate that I did, right? If, for example, the domain one itself spreads out, right? Then the area, you are multiplying by the area, right? R to the D minus 2 times the domain wall tension. So this will also increase. Then imagine that you have a domain wall of thickness R, right? Or R prime. Then the area that will multiply it by, that will also be R prime.
Yeah.
right? So that in that sense, so yeah, so the R prime can be much larger than that because then all these estimates is R prime which will enter.
So slow variation will not decrease that much. Yeah,
Slow variation will decrease, but will decrease only by a factor of 1 over R at most. Right? That's the point. That's it. So slow variation. So if you do slow variation, what happens is domain wall tension will become grad phi square times dr across in this region, in this direction. So that's rough estimate is r to the minus 2 times r, that goes r inverse. So the energy will be r inverse times r to the d minus 2. That's the idea. In fact, the correct way to estimate this will be that it's grad phi square times the volume. Right? So 1 over r square times the whole volume, right, which grows as r to the d minus 1. So basically at the end you get r to the d minus 3, right? Whether you count it as the domain wall tensor times the area or just the energy density times the volume. Right? The energy density times volume will be r to the minus 2 times r to the d minus 1. Okay? So that's also r to the d minus 3. So with this, if you calculate the short cell radius, right, again by using e to the 1 over d minus 3, you see that it grows as r. Okay, so the short cell radius and the size of the system are of same order. That's the maximum, that's the best you can do.
And local time evolution will be very slow because though there's variation, it is very small variation.
Exactly, right?
So a Banks' situation, I think, imagine just being constant.
Yeah.
So that was not evolving at all for a while.
Exactly.
Yeah, it's evolving, but very slow.
That's it. Yeah.
Okay.
Okay, and again, if you fix your accuracy and then you can just make it
Right.
as low as you like. Okay, so the point is that here RS is the short cell radius is growing at the same rate as R. Right? So we need a more refined analysis, right? We cannot just based on the scaling argument to decide whether it is possible to have measure everything in B or not.
So if RS were to grow slower than R, then the argument would be that I do the experiment just outside the
Exactly.
horizon.
Exactly. Then the argument will be you do the experiment just outside the horizon. In fact, if RS was smaller than R, right, then probably there is no RS in the first place, right? Because this is assuming that the mass is the whole mass, right? So if when we estimate RS if it's smaller than R, then most likely there is no horizon.
Like the sun.
Yeah, exactly the sun. Right? The sun has a RS which is much smaller than the radius of the sun, right?
So sorry, what's the precise link between this experimenter and this laboratory thing and saying that this moduli is a state in the space or not?
Yeah, so the link is that so this is how we define, right? That we'll say that B is a state of A. If any experiment that you can do in B, right, can be performed in A. Okay? And if we can create a large enough region, right, for large enough time scale, right, where the environment is the same that is arbitrarily close to that of B, then that allows you to do the experiment in that environment, right, and then transmit the data to A, to the asymptotic observer. So then we can say the asymptotic observer has an access to anything that we can measure in B. Right? So that's the sense in which we'll say that B will declare that B is a state of A if we can create an arbitrary large region where the environment is that of B. Okay, so this is a refined analysis that we'll have to do, right? And that we'll do in a few minutes. But now let me give the second argument. Yeah, this is an ADS, and this is certainly more convincing that in ADS case. In ADS, the asymptotic values of the moduli set the coupling constant of the dual CM. So if we take, for example, type 2 beyond ADS 5 times S5, then the value of the dilaton or exponential of the dilaton, phi is the dilaton, right? The exponential of the dilaton at infinity gives the square of the angle sum. And here, clearly changing the Young-Mills coupling will take us to a different theory, right? This nobody disputes that if you have n equal to 4 super Young-Mills with coupling constant G Young-Mills, right? Then if you change G Young-Mills, right, it's certainly a different theory because you are changing the coupling constant of the theory.
So that's the different boundary theory.
It's a different boundary theory.
But your description should be applied to the bulk theory.
But boundary theory is supposed to be the same as bulk theory, right? Anything that you can measure in the bulk theory you can measure in the boundary field or vice versa.
But this definition may not simply translate in the same way, right? Because definition involves some region and so on. But if you're that region,
That is true. But this you can forget about the region, right? What this is saying is that is it possible that if you have a theory of coupling constant G angles, you can measure anything that you can any this S matrix, for example, like at any other value of G angles by staying in that field. Right? And in general, we believe that that shouldn't be possible, that different coupling constants are really different fields.
But naively, wouldn't it be like adding some F square term?
Yes,
But
true.
that takes infinite energy.
No, okay, so take a volume, and you are right that you can take a volume and you can add integral F square, right? But that is not a state in the theory, right? In fact, this is the basis of this Rees writer, that if that was a state, if you could create that state, right, then you could destroy Andromeda galaxy by sitting in this room, right? Or you can create 1,000 other galaxies sitting in this room, right? So because it's not a unitary transformation on the vacuum, right? So adding integral F square, right? It is true that that changes the coupling constant, but that we cannot think of as a state in this original theory. Right, because it's not a unitary transformation.
But sorry, I mean, in ADS5 at a very small scale, I could change the string complexity, right, or the coupling.
Very small scale, yes,
Yeah. So
but not an arbitrary large scale. Right. So the point is here, the idea is you have to be able to perform any experiment that you can do in B inside X, right?
I see.
And the point here is that the volume grows very fast with radius. Is that from the
Yeah, that we'll use a scaling argument to stretch out the solution, that make it as smooth as you can, right? And that will fail in radius.
So you will lose that factor of R. Of that.
Not exactly factor. We'll see how this works, right? How the argument goes, right? And then it will become clear where it fails in radius. Okay? That we'll have to stretch out. We have to make things as smooth as you want, right? And as you try to do that, this fails in ADS because of this cosmological constant. Okay, so here is the strategy.
so now you're going to now you're going to give a detailed kind of strategy
Exactly.
to show that which way they require. But at the naive level, is there a problem in ADS? Here you show that at the naive level it was touch and go. Like it
Yeah.
could have gone either way. Is that the same in ADS or even?
I think it is the same in ADS. I mean, the scaling argument is basically that, right? We'll see the scaling argument. It's a cosmological constant, right? That you can change things at a scale which is smaller than the sub-ADS scale.
Yes.
But in super ADS scale, this becomes a problem.
But that you would be able to see even naively, even just by seeing how volumes and surface area scale.
Okay. One naive argument, right? Which is that in ADS, the light crossing time is finite, right? So if you create a domain wall, right?
You'll never be able to do any.
It will collapse in ADS time, right? At least the signal from far will reach the detector within ADS time scale, right?
I see.
You cannot have an experiment that survives for more than ADS times.
I see. So the dynamics is such that it takes it.
Exactly.
I see.
Yeah.
I see. Yeah. Thank you.
Okay. So here will be the strategy. Okay. That the first point is to observe, there's an observation, and this is generally true, and I'll show in many examples, that charged black hole solutions typically have varying mode. Right? You construct a charged black hole solution in theories which are moduli fields, and find that the scalars, right, actually vary as you move around in the background of that. Right? Asymptotic value of the scalar is different from the value near the horizon. Okay. And if you add rotation, then it can even depend on the angle, the theta. So we can use charged black holes to create regions where the moduli differ from their asymptotic values. Yeah, this is certainly possible, and this will be possible also in any case, right? This part is the same. But this itself is not enough, because this does not necessarily produce an arbitrary large region where the moduli are approximately constant and all other fields are set to 0. Right? Because this is what you want to achieve. that we fix an accuracy, and within that accuracy, you have to make sure that the moduli fields are close to what the desired value be within that accuracy, and all other fields should be set to 0 within that accuracy.
So you want to use the charge black hole to engineer a particular modulus near its horizon, so that
Exactly.
it's
Yeah, it's horizon or somewhere in the radial direction. And that's what you want to engineer. Okay. But if you just take a charged black hole, typically the moduli are varying at a certain rate, right?
Rate set by the Schwarzschild radius.
Rate set by the Schwarzschild radius.
So if you just make it very large.
Yeah, basically that's what you have to do. Right? You have to make it very large. And this is what fails in ADS. Right? Because
There's another scale.
Yeah, there's another scale. Okay. So this is the second point, that any two derivative action admits a scaling transformation. Right? If you take a two derivative action of gravity, then you can show that there is a scaling symmetry in the action where you scale the various tensors by the rank to remain to scale by lambda square. If you have a k index object, right, say k form field, you scale by lambda to the k. So scalar, for example, doesn't scale. Right? Scalar has no vector index. Right? It's a 0 form, so scalar doesn't scale. And under this scaling, the action scales like this. Okay, this is not hard to understand because basically the lambda to the minus 2 comes because if you have two derivatives, then the two derivatives have to contract to g upper mu, right? Okay, and g upper mu scales as lambda to the minus 2. So that's the source of lambda to the minus 2. And lambda to the d just comes from the square root of determinant g. Okay, so that's this lambda to the d minus 2. So this means that this is not a symmetry of the theory, of course, because action changes. But this is a solution generating transformation. So this generates a new solution from the old ones. Okay, and it basically stretches both the radial direction, okay, the space and time. Right? So I'm going to one example, right? I mean in our normal space time. Right? If you have a merging black hole solution, right? Then given one merging black hole solution, right, you can generate another by if you scale the black hole masses by lambda, okay, the distance between the black holes by lambda, okay, and time scale you scale by lambda, right? That's an exact solution. Okay, so if you can calculate the gravitational radiation from a merging black hole, right, you can calculate also the gravitational radiation from a merging black hole where the masses are twice the size, the distance is twice, okay? And so what will happen is the gravitational radiation will just slow down by a factor of lambda. Okay, the wavelength will be stretched by a factor of lambda. So that's the scaling. That's the kind of scaling that we are going to use. So in this case, any invariant, right, that contains 2n derivatives will scale as lambda to the minus 2n. So for example, the Ricci scalar, okay, which has two derivatives, right, that scales as lambda to the minus 2. G mu nu del mu phi, right, which is the grad phi square, which basically measures how fast the dilaton is varying, the scalars are varying. That also scales as lambda to the minus 2. So these will all vanish as you take lambda to infinity. Right? It basically means that you make the solution, okay, all the variations, okay, become very slow by simply scaling up the black hole size. So if we apply this on the black hole solution, then we can create arbitrary large regions where the moduli is approximately constant and the space time is approximately flat. Right? Because imagine that earlier the dilaton was varying by say 1% within 1 centimeter. By stretching this, you can make sure that the dilaton varies by 1% over 1 million light years. So you can make the variation as slow as you like, and that's what to do to stretch out the solution, and you can create these regions, and then you can do your experiment in those regions. Okay, and under this scaling, the masses and the p-form charts scale like this. Okay, so this is the general idea. Now I will give some examples of how things work.
And you know this is not surrounded by a black hole because it is outside the black hole.
Exactly, because you explicitly have the black hole, right? Black hole horizon is already there, so you know that. So there is a black hole, but we are doing the experiment outside the horizon.
So it's really this fine balance that.
Yeah, exactly. So this is really explicitly we are giving an example where this fine balance works. right? And the horizon somehow is inside the region, right? We can do the experiment outside the horizon. Okay, so here is the first example. This is a black hole in type 2A string theory in 10 dimensions. So type 2A string theory in 10 dimensions has a U1 gauge field, and states which carry charge under the U1 gauge field are what are called D0 gates. Okay, so this is a Ramon sector U1 gauge field. So here is the solution. So R plus and R minus are two parameters. Right? So these two parameters basically determine the mass and charge of the system. Okay, some combination of R plus and R minus is the mass, and another combination of these the charge. So this is a metric that I have written down explicitly. This is how the dilaton changes as a function of the radial coordinate R. Phi naught is the asymptotic value of phi. You can see that R, as R goes to infinity, phi goes to phi naught. And then there is also an expression for the gauge field itself, which I have not written down because we will not need this. And this d omega h square that appears here is basically the metric on the unit h sphere. Right? So this is a 10-dimensional metric parameterized by the coordinate p, r, and the angular coordinates of this 8-dimensional sphere. And R plus is taken to be larger than R minus. Right? This is basically the BPS one. R plus equal to R minus is the extremal black hole, right? Where the horizon basically coincides with the singularity. So the extremal limit is singular. Right? R minus equal to R plus is a singular limit. When the horizon becomes singular. So our important point for our discussion is the location of the outer horizon, which you can actually see is at R equal to R plus. Right? This is the location of the outer horizon. And in the context of this solution, we can also see what this lambda scaling that we talked about earlier is doing. Right? You basically scale R plus minus by lambda, R by lambda, and T by lambda. Okay? And that basically multiplies a metric by an overall factor of lambda squared. Right? This is easy to see. Okay? On the other hand, the dilaton doesn't change. As you can see, to scale R minus and R plus by lambda, the dilaton doesn't change, and that's consistent with the fact that the scalars are not supposed to scale under the scaling. Now, these scalings, of course, can be undone by general coordinate transfer. Right? So, this is I have just done these scalings to show that the metric really picks up an overall factor of lambda squared. Right? But ultimately, we may want to bring them back to the original variables R and T instead of scaling by lambda. Okay. Now, the point to emphasize the following that we are eventually going to take R minus and R plus to be as close as you like. And we also want to take R to be close to R minus and R plus. Right? This limit is singular. But choose your R minus R plus and R, right? Arbitrarily close, but not on top of each other. And then the solution looks highly curved in that region. Now you do your lambda scaling. Right? Lambda is completely arbitrary. You can take lambda as large as you want. Right? Increase the mass of the lambda. That will smooth out the solution completely. Right? Even though you start from a very highly curved solution near the horizon, once you do this scaling, the solution becomes completely smooth. So you can go as close to the singular horizon as you like by scaling the solution up, by scaling to this parameter lambda.
You want to go close to a singular horizon so that you can make the dilaton very different from what you thought.
That's right. Right? Well, suppose you want to make the dilaton to be close to, suppose you want to make e to the minus 2 phi to be close to 0, right? Or phi close to infinity. Then you have to take R to be close to R minus, right? But R is larger than R plus. So you have to take R plus to be close to R minus and R to be close to R plus, right? In that case, if you do this for this solution, then the curvature becomes very large near the horizon. But however large it is, right, as long as they are not really on top of each other, as long as there is a slight difference, right, you can now scale by lambda to make the solution as smooth as you like. Right? And you can see that that doesn't change the delay, right? Because this ratio remains fixed.
Now, if you, and this is probably irrelevant, but if you really took the dilaton large, like order 1, then you want to You go to M theory, but that's not.
Yeah, we're going to go to M theory. Yeah,
Okay.
We want to go to M theory.
Okay.
So which is okay. So the point is that the dilaton goes through values of order 1. So the coupling is of order 1.
Yes.
Okay. But that doesn't matter because there is general argument that if the two derivative terms in the action are not normalized to any order in Potter-Wilson theory or even non-Potter-Wilson. Okay, so two derivative terms, and that's what you are using here, right? So the solution is not breaking down, even though as you go radially inwards, right? You can start from very weak coupling and it's going through a strong coupling of order 1 and stronger. Okay. But the dilaton is remaining of order. The curvature is still remaining arbitrarily small.
You will actually be going to M theory.
Yeah.
Right?
Yeah.
At some point, this thing is like wrapped around the M theory circle. At some point, it will clump, and all of that is not going to be important.
What will clump?
The solution. Let's see.
No, the reason that is not important is because of lambda scaling, right? Because imagine what will happen. Clumping means what? It will come from a single black hole, right?
Yes.
Okay. But the black hole size is scaled by lambda, right? So as long as the radius of the extra circle is not scaling by lambda, right? This clumping is not going to happen, right?
So your coupling is never lambda is the largest thing in the problem.
Exactly. Lambda is the largest thing in the problem, right? You can make this thing as large as you want, the radius of the M theory circle. Right? Nevertheless, because the size of the black hole is much larger, right? It's not going to come.
I see.
Yeah, so this is what I had said here, that from this we see that this e to the minus 2 phi lies between these two ranges, right? This was the asymptotic value, and this is the value near the horizon. And if we take r minus to r close to r plus, then the lower limit approaches 0. And that basically means that the phi, the limit on phi goes to infinity, right? So phi can be taken as large as you want. And e to the phi is the coupling constant of type 2 string theory. Okay, so this means that you can make the coupling constant of the type 2 string theory as strong as you want. And infinite coupling limit is what is called the M theory, right? In fact, the original definition of M theory is that it is a strong coupling limit of type 2 string theory. So this way you can get to the M theory limit. Okay, so that means that any experiment that you want to do in M theory, you can do sitting in type 2 string theory at weak coupling. Actually, just create this black hole, right? Do your experiment near the black hole, but the asymptotic observer is still sitting at weak coupling. Okay, so this, so basically by taking lambda to be sufficiently large, we can produce arbitrarily large, almost flat regions with any coupling constant phi between phi naught and infinity. Okay. So the conclusion will be that from the earlier definition, the type 2 with phi larger than phi naught are states in type 2 with phi equal to phi naught. Okay. And this includes M theory, right, which is the type 2 and the phi goes to infinity limit. Are there questions?
So I'm getting confused about this one. I'm probably being very stupid. But if we just take near horizon geometry of zero brains,
yes,
and you put them at some temperature, and you follow what happens as a function of temperature, then there is a temperature, and then at the horizon, the value of the dilaton is just given by the temperature. Right? And then there is a temperature at which this clumping will happen.
yes.
So I would have thought that if the dilaton was large enough, the clumping will happen. And
but it's not that it's the temperature and then the temperature of the black hole itself, right? So the black hole temperature is going to 0 because M is going to infinity. See, there's a competition between two things, right? One is the temperature because of the non-extremality, right?
You're scaling the number of zero brains also.
Exactly.
Now I get it.
Exactly.
I get it.
Because charge, you have to mass and charge are both scaling up, right?
I get it.
Yeah. Exactly.
I see.
So basically, if you want to form this black hole, right? I mean, what you can do is you just take a big astrophysical black hole and then throw in lots of zero brains.
Yeah.
Right? Then that will basically take you to extremal limit, right? And make it a very big black hole which carries a zero brain charge.
I see. I think from my point of view, all this happens with some scaling that involves some power of n, and that also you're also scaling.
Is scaling. Yeah. Exactly.
Yes. Okay.
Yeah.
I get it. Thank you.
Yeah, but lambda scaling automatically requires that, right? That you have to scale up the charge of that.
Right.
But it is still, you can do it with finite resources, right? As long as you don't demand that you get to M theory with arbitrary accuracy,
Yeah.
but with arbitrary large circle.
Why did you said that you don't demand that you get an arbitrary accuracy? I thought this was.
Yeah, arbitrary, but you have fixed accuracy.
Yeah.
Right? So you fix your accuracy.
Yeah.
Right? That tells you how large the M theory circle has to be, right? Because to get to infinite size, you have to put infinite zero branch charge.
Yeah.
But a finite size is good enough, right? Finite but large size. That's what you are saying here. Okay. So basically, this is another way we can take this, in fact, as a constructive definition of M theory, right? Because normally the way you define M theory is the infinite coupling limit of type 2A string theory, right? Now, if you tell an experimentalist that there is an infinite coupling limit of type 2A string theory, right? The experimentalists have no idea to see what it means, right? How can you change the coupling constant of the theory, right? But you can tell the experimentalist, okay, you take a astrophysical black hole, throw in lots of G0 brains, right? And then they do the experiment close to the horizon, and whatever you get will be by definition the S matrix of M theory. Then it is something that is measurable, right? So in that sense, you can think of this as a constructive definition that you say what experiment you have to do to prove M theory from the weakly coupled type 2 string perspective.
It's very close to matrix theory. That you can make M theory by putting lots of zero brains.
Exactly. Yeah. Yeah.
Very
But
close
here-
to Malthus
Exactly.
zero.
Yeah, exactly. Except that here you are not going near horizon, right? We want to think of this as really from far, right?
But you are, in the end, you're going near the horizon, right?
Exactly.
You're taking R plus near R.
Exactly.
So
Yeah.
it's very close to that.
Exactly. Right? I mean, the main difference we'll see. We'll also get ideas from here,
Okay.
right?
Okay.
The scaling will be different. So, yeah, you are right. It's close to matrix theory, not quite the ADS-CFT.
But it's close to, I was thinking ADS-CFT for zero brains.
ADS-CFT for zero brains. Okay, yeah.
Because you're really taking sort of near horizon geometry of
Yeah.
near
But
extreme zero brains.
we really want to take the infinity element here.
I get it. So a particular
Yeah,
element of that.
exactly. Yeah. Okay. So here is a second example. Okay, here you start from a 4-dimensional theory. So type 3 or type 2 is string theory on P6 times R31 or M theory on P7 times R31. Okay. So these are in fact the same theories. Right? Because by various string dualities, one can show that these are the same theories. Okay. Because M theory on S1 of course is the same as 2A. And 2A and 2B are equivalent once you compactify a circle. So these are same theories, but the solution that we are going to describe will be physically different. Okay, so let me explain what the solution is. So we are going to construct a black hole solution in this theory, which carries only momentum charge along the compact directions. Right? We will denote the compact directions by y, and you want to construct a black hole which carries only momentum along the compact directions. Right? Which means that for P6 compactification, we want to put 6-dimensional momentum along the P6, or for M theory compactification, you want to put 7-dimensional momentum along P7. And here is the solution. Okay, this solution in the two derivative theory also can be constructed explicitly. So I have given the metric, the 4-dimensional metric, which is here, rho t, and omega 2 is again the metric on the unit 2-dimensional sphere, d theta square plus sine square theta d phi square. So this is the 4-dimensional space time. We can see that there is a horizon at rho equal to 2m from here. And this is the metric in the internal space. R is a function of rho, which is given here. Alpha is just a constant parameter. N is a unit vector. And the physical significance of this N is that this is the unit vector along the direction of the internal momentum. And alpha is basically the magnitude of the momentum.
So you can get the solution by uncompactifying, boosting, and recompactifying.
Yeah, in some sense. Yeah. You can get this uncompactifying boosting. This is like a PPO solution, essentially.
Right.
Yeah. Okay. So the moduli information is hidden here. Right inside this. Because this is the internal vector. Right? So that's what contains the information of the moduli of this theory. And again, we can do the lambda scaling. Right? The lambda scaling will correspond to basically rho T m by lambda. Right? If you do that scaling, you can see that the metric just scales by lambda square because this ratio doesn't change. T scales, rho scales, and we have also rho scales. The scalar fields don't change, right? Because the internal metric under this scaling doesn't change. R, you can see that as since rho and m both scale by lambda, R doesn't change.
So in the model, then you mean the shape of the torus?
Shape of the torus, yeah, shape and size of the torus. Okay, which is basically here in this. Okay.
In a simple analog, if it was 5 to 4, then this would just be the size of the circle.
Exactly.
Right.
It will just be the size of the circle. Okay, but here there will be some
Complicated.
not complicated, but for some further subtleties which you will see.
I see.
Okay. So yeah. So you can see that here, okay, R varies with rho, right? So as you change rho, you can get different R, which means you can get compactifications of different radii. Okay, because the size varies, and you can then by using this black hole solution, you can produce different values of the internal size of the torus, okay, simply by working with different values of rho. Okay, but we'll also look at the extreme limit, right? Where we take alpha to be large, and you can see that if we take alpha to be large and rho to be of order m, then R becomes large. Okay. So effective theory is decompactified, right? The radius is become size of the system is becoming large. So the question is how many directions decompactify, right? If we take R to be large. Now, if you look at this, then it looks like apparently only one direction decompactifies, right? Because the direction along n is becoming large, right? The transverse directions will remain finite size. But it turns out that if we choose this vector n properly, right, then effectively all the directions decompactify, right? And I'll try to see why this is the case. Okay. So the claim is that by choosing n appropriately, and then by taking alpha to be large and rho to be of order m, we can get to a limit when all the circles have become large.
So could I think of your previous example as an analog of this, but it's going from 10 to 11?
Exactly.
But it's just one circle there.
Exactly.
Now,
Here is you are making everything large. Okay. So here is the internal metric, right, which you can see. Okay. And let's suppose that y, of course, is a periodic variable. Let's suppose that each yi has period 1, right? Actually, we start with that internal space. Okay. Each yi has period 1, and then you have a metric like this on the internal space. Okay. And you are trying to determine how many directions become large. Okay, as I said, naively, it looks like only one direction becomes large, but that's a direction parallel to y, where that's getting scaled by r square minus 1. All the other directions are remaining a fixed size. But what we need to check are the sizes of the cycles, right? Not arbitrary directions. The arbitrary directions are not periodic directions of the torus, right? We have to look at the cycles. So cycles are what? Cycles correspond to shifting yi by integers. Okay, because you come back to the original one, right? So you identify the various cycles and see the sizes of each of these cycles. So the size of a cycle like this, yi going to yi plus mi, is given by this. Again, it just follows from this, right? R square minus 1 times n dot m square, and dy square was basically becomes m square, because you are just considering straight lines on this space. And you want to see if we can get full decompactation. So to get this, we choose n to be of this form. N is a unit vector, okay, so you have to of course normalize, and we take c to be r to the minus 1 over t, okay, where d is the number of compact dimensions, okay, so this is a d-dimensional vector, and we take the vector n to be of this kind, okay, with C scaling like this. Okay. And with this, one can easily check that in fact all the cycles become large. Okay, and the way we see this is the following, that imagine that we take that in order for a cycle to be to a finite size, we have to make sure that this is zero, that this part doesn't contribute, right? Okay. So you want to make n dot m equal to 0, right? What n dot m is basically this multiplied by mi's.
Sorry, why do you want that part to be 0?
This part, because otherwise it's a large cycle size anyway, right? R is large, right? So we are trying to see if we can make any cycles finite, right? In this, because we are going to argue that all the cycles decompactify, right? If you want to prove the opposite, right? I mean, we'll assume that some cycle remains finite, and we are trying to find that cycle,
Okay.
right? So let's suppose that there are some choice of mi's, right? For which the cycle is finite,
Okay.
right? So in that case, this has to vanish,
Right.
right? But n dot m is m1 plus c times m2 plus c square times m3 and so on, right? So to make this 0, you have to make cancellation between different terms, right? In order to have a cancellation between different terms, right? I think you can easily see that at least one of the mi's should be of order C inverse. Otherwise, how will you cancel, right? But if any of the mi's is of order C inverse, right, then this term becomes large.
You scale C to be large, you say.
We scale C to be small.
Small. Yeah.
C to be small, right? C goes to the minus 1 over T. So this basically shows that it's impossible to find a cycle which has finite size, right? Either this term contributes a large number or this term contributes large number. So this limit everything decompactifies, right? So which basically means that we are going back to the decompactified theory if we take this limit. And you can of course get various other values on the moduli, but I am just giving an example, extreme example of what you can get from this compactified theory.
So when you started this, I thought you were going to use some irrational something.
It's like irrationality.
Yeah.
Well, see, I mean,
If the denominators become yes.
exactly, meaning
Very large.
you could do some argument like that, but
Yeah.
then you have to go into number theory.
Okay.
This is much simpler to see, right? You don't have to invoke any number theory for this,
Okay.
right? But it's basically that thing that you want to go at an angle,
Yeah.
right? And what I'm doing is I'm going at an angle which is very close to grazing the one of the lattice vectors,
Yeah.
right? And that's what is making it hard to
Yeah.
get finite
Yeah.
cycle size. Okay. So the conclusion will be that type P on R91, 2B on R91, and M theory on R101, right? The decompactified theories are all states in P on T6, right? Because you can start with P on T6, right? And get all of these by appropriate limits. But the black holes that we use will be different. So to get P on R91, we need a black hole that carries large momentum in all the 6 directions. To get M theory on R101, we need a black hole that carries large momentum charge along all 6 directions, but also large d0 plane charge, because d0 plane charge is the momentum along the 7th direction. Okay, in this language. And to get type 2B on R91, we need a black hole that carries large momentum charge along the 5 directions and large winding charge along 1 direction. Because winding charge in 2B becomes the momentum charge in 5. Momentum charge in 2B becomes winding charge in. So these are all from the perspective of type P on P6, right? What you have to do in type P on P6 to get these theorems.
Ashok, sorry, going back, so why are we looking at this two derivative action complements?
You don't have to, but the point is that even if there are high derivative corrections, once you do the lambda scaling, right, those corrections all go away, right? So the hard derivative corrections can be ignored in this lambda scaling. Right? Because you are really going to the limit where the black hole becomes very large. Okay. So now the next point, which I have already said earlier, is that this lambda scaling can also be applied to time dependent. Okay, the black hole is of course time independent background, but imagine that you have a time dependent solution, right? Two black holes merging together, okay? Which is normally not the setting in which you do your experiment, right? But if you think of that we are merging with Andromeda, right? We are doing our experiment in LHC very well, right? Because time scales are so small so large that it doesn't affect us. Right? So we can take a merging black hole solution, right, which has a more complicated pattern of solutions, pattern of moduli dependence. But as long as you scale it up by lambda, we can do your experiment there because that configuration is going to survive for time of order lambda. Right? And by taking lambda sufficiently large, you are allowed to use those backgrounds also to do the experiment. Okay, so and these can be used to generate new backgrounds, and this is in fact necessary. If you want to try to argue that all points in the moduli space can be generated, right? You have to use this kind of time-dependent background, right? Just static black holes are not going to do the job, right? And I'll give some examples why we need these time-dependent configurations. Okay, so here is the first example. Take type 2B string theory 10 damage. And it has a dilaton. So I would like to see if we can, that starting from one value of the dilaton, if we can produce regions where the dilaton takes a defined value. Okay, because you have to argue that all those points are actually states in the original theory, right? So we should be able to produce large regions with defined value of the dilaton. But type 2 string theory doesn't have U1 gauge field, so there's no black hole. There's no charged black hole, right? So you cannot use the charged black hole to construct varying dilaton solution.
Sorry, just before this, Ashok, you argued that these compactified theories could be used to construct the decompactified theory.
Yes.
Was there an argument for the other way around?
No.
In the two-way situation?
No.
Okay.
So lower dimension seems to be better. That's the statement that it doesn't go the other way.
Right.
So starting from lower dimension, you can go to higher dimension, but the other way seems harder.
And that you believe is a fundamental thing, or it's that you haven't yet found a way, or you think it's real?
Yeah, I don't know. I mean, it seems to be much harder, right? I'm not saying that it's not possible, right? But it certainly seems much harder. Right? And as I said, this, I mean, I think it is more or less clear that this is not reversible always, right? There are certain examples when you consider ADS solution, for example, right? That it's hard to see how we can reverse it. So I think this may be fundamental, that not everything can be constructed for everything else, right? But starting from lower dimensional theory, you can probably do construct higher dimensional.
But suppose you want to start from a big, just the same dimensionality, but a big radius and go to a small one. Your examples were starting from a small radius and going to a bigger one.
Yeah. So that I'm going to discuss. Right? Yeah. That I'm going to discuss. So okay. So this is the first example, right? So here you don't even have a way to use black holes to vary moduli. Right? But what we can do is to use various other branes. Right? Now, other branes means what? It's a fundamental string. Right? That's a brane. But you don't want to use infinite fundamental string. Right? That requires infinite resources, right? Infinite energy. So you don't want to do that. But you can take a fundamental string and take a large loop. That will produce varying fields, varying moduli. And now the idea is that if you now carry out this scaling, right, make the fundamental string very large, then the variations of the fields will become arbitrarily small. And you can use that configuration to do your experiment. The only difference from the previous one is that the fundamental string, of course, is not going to last for long, right? Not for arbitrary long, but it will last for a time scale of order lambda, right? And that is good enough. Yeah, because you can make lambda to be arbitrarily large. Okay. And instead of fundamental string, you can also use various branes, right? D3, D5 or D7 branes you can wrap. And you can, well, wrap meaning again to make it finite mass. Okay. Because you don't want to use infinite D3, right? But you can use some spherical shape D3. And then you can produce varying coupling constants and do your experiment.
And this you say will change in ADS. This will change in ADS because they will collapse very fast.
Exactly, yeah. This will change in ADS, right? Because they will collapse very fast. Even the other scaling, right? The black hole, right? There, of course, is static. So this problem of collapse is not there, right? But there, what will happen is that at least the scaling it doesn't work anymore, right? Because once you start to scale it up, once you go beyond ADS scaling, I think things get frozen.
I was wondering whether you can generate the physics of an n+1 dimensional Yang-Mills theory in an n-dimensional theory by making an anti-D3, a large anti-D3.
Yeah.
And that I think you'll say will collapse very fast, right? Or not?
Also, I think it will be enclosed. It will be enclosed inside the black hole horizon. I think in Poincare patch it's easy to see, right? In Poincare patch, what you have a stack of you have a flux, right? Which means the n D3 blends. You have converted to flux, and you are now constructing an anti-D3 blend, right?
Yes.
So this is n plus one D3 and one anti-D3, right? But this, from the asymptotic observer's perspective, is a non-extremal black hole, right? So there's a finite horizon, right? So in the scaling limit, basically the horizon encloses this system.
Because it's infinite, you're saying. No, but
Because if it's infinite, yeah.
I see. I see. You could move this very far away though, initially. It doesn't matter, you're saying?
I think it doesn't matter.
Because it's an infinite system.
Yeah, because it's an infinite system.
Okay.
Yeah, so I think it's not. Yeah, I mean,
I see.
that's my understanding.
I see. And ADS also it would be very easy to estimate, right? Because the surface area looks like volume.
Yeah.
And we could just quickly estimate the energy and check.
Yeah. Okay, so this is basically the point that you can use. So in type 2 string theory, you can produce varying dilaton by using these higher bands.
Sorry, Ashok, but of course it's possible to produce the physics of an n-1 dimensional universe.
Yeah, because
that
in Poincare patch you can certainly do it because that's a BPS configuration, right?
And even in spherical,
in the spherical,
very little away from
exactly. Yeah, it will evolve, but it will evolve slowly. Exactly. Yeah. So that is consistent with the gauge theory expectation, right? That starting from UN, you can produce UN minus 1, right? But not UN plus 1.
Yeah. Okay.
Somehow the formation of black hole horizon or this collapse seems to be correlated with what you can possibly do in a gauge theory.
Interesting.
Right? So that's why I don't think that these are unrelated observations, right? Even though they look different observations, right? They're probably correlated. Okay, so this is example 2 that what I wanted to know how to get to smaller areas, right? Which means in terms of coupling, we want to reduce the coupling. Right? So if you go to type 2A on R91, right, the D0 blend black hole that we constructed, that we saw that it allows us to create regions which are larger than asymptotic, right? But not lower than asymptotic. It allows you to make regions at phi varies between phi naught and infinity. But if you want to make phi to be smaller than phi naught, right, what you can do is to use spherical D6 or D4 blends. Because near the horizon of near these, we know that the coupling constants are actually smaller than the asymptotic values. Right? If you take a flat D6 blend solution, okay, that solution is known and the phi actually is smaller, becomes smaller as you go towards the horizon. Okay. Now instead of taking infinitely flat, you just take a spherical object. Okay. But as long as the spherical object is sufficiently large, it's almost as good as flat, and you can do your experiment in the neighborhood.
So instead of doing ADS-CFT in a brain where the coupling constant becomes strong in the IR, you look at do ADS-CFT in a brain where coupling constant becomes strong in the UV.
Exactly. Yeah.
And once again, here do you need to go near to the near horizon limit for this?
Well, depends on how far you want to go, right? If you really want to go to zero coupling, then you have to go close to the horizon. If you just want smaller coupling, you don't have to go all the way to the horizon, right? Because the phi is varying continuously between the horizon at infinity, between phi naught and minus infinity.
Okay, but I see. You want the decoupling limit to get a large running thing.
See, any phi that you identify, right?
Yes,
that can be smoothened out because in the lambda scaling limit, when you take lambda scale by lambda, right? Every region is infinitely expanded, right? So any coupling that you can identify, you can make it constant for arbitrary large regions.
Basically, you want a very large running between the place where it goes from flat to nearly the near horizon region, and to the horizon.
Exactly. And then you just stretch out the whole thing.
That whole thing,
right? So that the variation is arbitrarily slow all. Right? Because in this the geometry is
for the coupling, that stretching doesn't matter.
Exactly.
The ratio of that coupling is independent of that stretching.
Exactly.
So
exactly.
You get the ratio you want and then stretch it.
Then stretch it. Exactly.
The lambda scaling also applies to the size of this.
So the size also becomes larger. Exactly. Right? Because the whole solution becomes larger. so the size certainly becomes larger. And I had given the scaling of the p-plane charge also. Yeah. That for a p plane, you have to scale the charge also. Right? So for example, for a string in 4 dimensions, right, problem P is equal to G minus 3. Right? The charge of the plane doesn't scale. Right? A single string is good enough. Right? That will, as you scale up the single string remains a single string. Otherwise, you have to take multiple planes. Right? And that number has to be scaled up.
So the fact that that is discrete doesn't really.
Yeah, because you can always take lambda to be discrete. Yeah, that is the D0 plane charge is also discrete, right? But you can scale it nevertheless. Okay, so here is how to get ADS. Right? Again, we start with type 2 on T6. This is the example I discussed. Right? And we saw that we can go to appropriate regions where we can get type 2B on ADS 5. So we can get type 2B on flat space, right? That we saw. We can expand it out. Now the idea is that first we do that. First we'll do whatever I described earlier, right? Make the torus size in 2B or PM or M theory large using a large black hole. Then to get type 2B on ADS 5 times S5, we wrap n difference along a T3 in type 2B on T6. Right? Along one of those, 3 of those 6 circles, we now wrap a n difference. Okay? But this time we don't scale it. Right? As you used to scale lambda, you don't scale n. Right? You keep a fixed n. Because if you scale n, you will get flat space again. Right? But if you keep fixed n, you are going to get ADS 5 times S5 within your horizon geometry. Right? So you can create this configuration in type 2B on T6 times R31. And any experiment that you can do in ADS 5 times S5, you can do in type 2B on T6 times R31, right? By creating this configuration and sending out observers near the horizon. Okay. And here again, the point is that you cannot go, you can go arbitrarily close to the horizon, but not all the way to the horizon, right? Because you want to send your signal back. So it's not, because ADS, the ADS 5 times S5 has an infinite throat, right? So you don't go all the way down the infinite throat, but you go sufficiently close so that you are within your experimental demand. Okay, you do your experiment and then you can send back the signal.
So the way ADS CFT gives us this duality, this other types of scaling also, is there a way to kind of have this? I mean, does this tell us about some relation between the?
See, other type of scaling is basically that it is saying that you have to take the large n limit to get to flat space. Right? Which you know anyway, because, but I mean, it's not completely clear what that means, right? From the gauge theory perspective, but from, if you have an observer in type 2 on T6, right? That person knows what to do experimentally, right? What to build and what to measure.
But even the gauge theory can probably do the same. It focus things at that region of space.
But you cannot change n. See, for a given gauge theory, you cannot change n, right? Yeah. So certainly for large enough n, you can do the experiment to good accuracy, but not infinite accuracy, right?
Yeah.
But once you have fixed n, then you are limited by how accurately you can do this experiment.
A meta gauge theory, one who has access to all n.
Yeah. But that's not a theory, right? So that's the point. That so flat space that way seems to have more flexibility than ADS. Nice. Okay. So basically, I've said that all of these, right? I mean, all of these backgrounds you can produce in type 2 or T6, right? So basically, this is saying that all of these backgrounds and also states in type 2 or T6.
And for this question, you say it's not reversible. So you start with ADS and you want to get flat space.
Yeah, it seems very hard, right? Start with ADS with a fixed n.
Yeah.
Right?
Yeah.
So it's like, because I mean, the way you can think of it geometrically, it's like a wave, right? ADS is like a wave. There is an infinite throat, right? So from outside the well, you can go close enough and come back, right?
Yeah.
Send back signal. But once you are all the way into the well,
how do you ever go out?
Yeah, you cannot go out. This is what I have said here. Okay. That if we start with straight on an ADS space, we no longer have the solution generating transformation because of the scaling. We don't have the lambda scaling anymore. So you cannot create large regions where the moduli take values different from the asymptotic values, and this seems to be consistent with the argument of banks based on the CFT dual. Right? The fact that in the dual CFT, certainly changing the coupling constant looks like it's going to a different theory, right? It's not different state of the same theory. So somehow it looks like straight for an ADS space loses sight of the big picture, right? The fact that it's part of a big theory, it doesn't really know, right? It just knows about that particular theory, right? Whereas flat space somehow has the big picture in mind.
Again, very similar to ADS CFT. Like you can start with string theory, take a non-extremal limit, and take a scaling limit to get a theory on a brain.
Yeah.
But
coming back is very hard. Yeah, exactly. Right? With a finite number of brains.
Right. And with an infinite number of brains, you can then make little patches of that space and focus on that.
Yeah.
But you still don't come out in some sense.
That is true. Yeah.
You get it in another way.
Yeah. You can get to near flat space, right? Because it's not clear how to get to other backgrounds.
Right. You can get to exactly.
Okay. So here is basically the conclusion of what I have said so far. So in flat space-time, black holes or black brains allow us to create large regions in space-time where the moduli take values different from the asymptotic. And this is something that I have not proven, right? But it seems likely that all the moduli values can be reached this way. Okay, but we don't have a complete proof, right? So basically the idea is that for high dimensional cases, it's clear that you can do it, right? Because in take type 2 in 10 dimensions, right? We already saw that all values of coupling lower than phi naught, all values of coupling higher than phi naught you can get from a D0 brain, black hole, right? And using these brains, you can also get values of phi which are smaller than phi, right? So you can span the whole coupling constant space.
So if you start with M theory, then
if we start with M theory, then it's not clear how to do, right? That's why I said that it seems to be easier to go to higher dimension from lower dimension than the other way, right? Because how do you compactify one dimension, right? If you start with M theory on a big circle, then I think you can do it, right? You can do the reverse. But if you start with M theory in infinite space, right? Then
so even with these M2 brains and M5 brains, they don't have in the same way the D4.
No, I think the compactification here, if you want to compactify the tangential direction, you have to put it in. Right? Because even M2 and M5 are really infinite dimension, right? In this case, it is the examples that I described here, they are compact. Right?
Yeah.
But those compact directions are big. So if you want the M2 and M5 in non-compact space-time, right, which is what you want.
No, I mean just this is spherical M2 thing.
Oh, if you make spherical, but those will not be really compact space, right?
No,
Because see,
why do I need compact space? I just need to create this region which looks. How
How do you make the circle? How do you
make the circle?
Yeah.
That's the point.
Right, okay.
Right? Maybe there is a way to do it. I'm not sure, but at least it doesn't look very simple to do it.
Okay.
Right. So going to decompactification seems much easier in this picture than compact.
Sometimes orbifolds, space looks like this, no circles, but you have singularity which if you resolve, develop some circle.
Yeah, it may be possible with some complicated construction that you may be able to produce circles. Right. I have not seen how to do it systematically.
Ashok, so far you were talking about these moduli fields. But now suppose you've got another field that is another vacuum which is through a barrier.
Yeah. So that I don't know what to do.
There it feels like Banks' argument would be correct.
At least I think. Yeah.
That because it would really be like a
That's
small thing.
Yeah.
And there it feels that his argument would say that it's much harder to get to it.
Exactly. Yeah. But I have a feeling that if it's another vacuum which is lower, it may be possible to get.
Okay, I
right?
get your point.
So ADS, from flat space, you can probably go to ADS.
Where you can decay to it to start. You can decay to it.
Yeah, exactly. You can decay to it, right? Even if you cannot decay to it, you may still be able to produce it. Because sometimes the supersymmetric and if you have a supersymmetric flat space time, right? And there is supersymmetric ADS, then they don't decay into it.
Right.
Flat space time doesn't decay into supersymmetric ADS. But nevertheless, something like this may be possible.
Nice.
That you may be able to create entities.
Nice.
De Sitter is unstable anywhere. So maybe there is some relation that you cannot produce de Sitter for arbitrary long time anywhere, right?
But I was thinking of two zero energy vacua. Suppose you have two zero energy vacua separated by a barrier. For that, Bank's arguments seems to be exactly right.
On the other hand, maybe the string theory doesn't have those.
Maybe that's
right.
There are no examples.
So okay, there are examples from moduli. If there are it's not clear that there is a barrier, but n equal to 2 and n equal to 4, right? And n equal to 8 supersymmetric. All have moduli space. I don't know how to connect them. Right. So starting from an n equal to 2, can you produce n equal to 4 and n equal to 8? Right. This I don't know right now. Yeah.
Okay.
How to do it? Yeah.
But you believe that in string field theory, these formal arguments that one vacuum is the background of another, that would apply to these n equals 2, n equals 4?
So they are also, it's only marginal.
Only marginal,
right?
Okay.
So the point is that this kind of argument, right, allows you to change the unbroken number of unbroken supersymmetries. This kind of argument, so that there may be a pathway to where you are to go, because breaking supersymmetry requires that you put some extra brains which break the supersymmetry, right? Restoring supersymmetry basically means that you just flatten up some directions, right? So it is possible to change the number of unbroken supersymmetries. So you can start if A has certain number of unbroken supersymmetries, B may have more or less number of unbroken supersymmetries, right? Just by flattening up some directions or putting some brains which break additional symmetries. Right? But this one is an example, right? This one, type 2B on ADS side times S3 times T4. These are less supersymmetric, right? Than type 2 on T6. Right? Type 2 on T6 is maximal supersymmetry, this one is not. Okay? And it's not inconsistent because you have broken the supersymmetry by putting some D1 brains and D5 brains. Because it's not completely inconceivable that you can jump, but certainly I don't know right now how to do this, right, between different moduli. It could also be that when they are not in the part of the same moduli space, right, the criteria itself may have to be modified, right? What you mean by B being part of it. Right, but I don't know. I mean, it's completely open at this stage. Okay, so let me just finish by giving some open problems. Okay, this one I have already said that if we take compactifications that preserve 32 and 16 supersymmetries, like type 2 on T6 times R31 or heterotic on T6 times R31, is it possible to produce any point in the moduli space starting from a given point? Okay, by using these brain and black hole configurations. This, I believe the answer is yes, right? But although, because we have a lot of freedom, right? Because you can use black holes, black brains, various kind of brains, so there's a lot of freedom, and so most likely the answer is yes, that you can get to from any point to any other point.
So to understand the question, you're saying for all type 2 theories on T6 times R31, can you get from one to the other?
Exactly. Yeah. Right? Because type 2, I think it has 70 moduli probably. This is 70 dimensional moduli space. Right? Using brains and black holes, can you reach all the full 70 dimensional moduli space, right? In some region of space time.
So whatever you have done, there you showed that the little moduli can be reached anywhere.
Yeah, exactly.
Not any other moduli corresponding to.
No, compact moduli also I need, right? That second example, right? The T6 moduli I could change, right? So certainly, I mean, changing moduli is not a problem, right? All moduli can be changed. Whether you can access every point in the moduli space is the question, right? Because once you have black holes carrying various charges, right? Typically, all the moduli start varying.
Ashok, this radial direction is exploring some particular direction in the space.
Yeah.
And the question would then be whether this, I mean, it looks like there's some cone kind of structure, right? And whether.
Yeah. So if you use spherically symmetric configurations, then the radial direction and the charge vectors, right? For the black hole. Right?
Right.
If you use rotating black hole, then also the theta angle, because things depend on theta angle, right? But on top of that, if you start using branes, then there is much more freedom, right? And you can take multi black holes, for example, right? Or branes and black holes. So all of these, right? Once you do the scaling by lambda, these are just very, very slowly varying configurations, and all of these can be used. And that's why I feel that this is probably possible. That you can probably produce such configurations. The second question, which is perhaps more interesting, but again, I don't know how to answer this, is whether you can prove similar results for compactification with H supersets, right? Like type 2 on Calabi-Yau threefolds. So here there is an interesting conjecture that moduli spaces of all Calabi-Yau threefolds are connected via this Flop and conical transitions. Right? So because even Calabi-Yau is a different topology. Right? Normally you think of the Calabi-Yau topology being unchanged, right? As you vary the moduli, right? But there are certain mechanisms, this Flop and conical transition, which basically says that the Calabi-Yau moduli space is connected. Right? The fact that I don't think it has been proven that all Calabi-Yaus are connected, but many of them are.
Sorry, but this means this Flop and conical transition. Why does it mean that it's connected? I mean, it's still this topology change, right?
Yeah, but it's connected in the sense that as a quantum field theory, as a scalar field theory, it is connected.
But this is more like these two vacuum that Shiraz was talking about, which is not marginal deformation, but rather same energy but separated.
No. Because at the conifold, what happens is that the way it happens is that you have a vector multiplier scalar, say phi. So there are two scalars, one real scalar, one complex scalar. And you have a potential like phi h square. Okay. So if you take phi equal to 0, then h is a modulus. Right? If h equal to 0, then phi is a modulus. Right? These are the deformed and resolved conical directions, right?
And then you can change a parameter to positive to negative, so that right.
Yeah, you don't do that. These are all the parameters. You don't have no other parameter, right? In the moduli space, so phi is part of the moduli and h is part of the modulus. The point is when you make phi equal to 0, you can start.
Yeah.
So they're connected through both equal 0.
Exactly. They are connected through both equal to 0, right? So in that sense, the moduli space is connected, and it's not inconceivable that in space time you will be able to produce configurations, right? Where these two branches get are connected with each other. Right? So if we can do that, then maybe it will be possible to produce a space-time background in which type 2 state in any Calabi-Yau threefold is present in some corner of space-time. Right? I mean, it's like a big space-time where you go into various black holes and black brane directions, and inside these you will find any Calabi-Yau that you want. Right? So all Calabi-Yau threefolds will be part of this same space-time.
And the asymptotic in that case should look.
Asymptotic may be one Calabi-Yau. You can start with one Calabi-Yau.
One very special Calabi-Yau, which
it may not even be very special, right? One particular Calabi-Yau, and then you go from there to various other Calabi-Yaus by using these branes and black holes.
But this irreversibility means that there is some speciality to that. Right?
Yeah, but in this case, I think that as long as they are part of the same moduli space, it may not even be irreversible, right? This problem comes only when you take the limit, right? It's like when you take really the M theory limit or the decompactification limit, then you cannot come back, right? Or you take the ADS limit, then you cannot come back. But I think within as long as there are finite points in the moduli space, they are probably all reversible, right? You can probably go from one to the other. That is my feeling, but again, I don't know. I don't have a proof of this. And this, I think, is what somewhat in the spirit of what Shiraz was saying. The factor with flux or different number of supersymmetries, right? This I don't know, but it's possible that this is also that one may be able to get there, right? Certainly, ADS5 comes S5 has flux, right? Which got it from flat space time background, right? So maybe it's possible that we will be able to switch on fluxes and get the flux vacuum. That's it.
Ashok, can I ask a question? Can you hear me?
Yeah.
Hi. You talked about T6 compactifications, but never talked about lower dimensions. What is apparently from what you say, it's hard to get to say 3D or 2D compactification starting from 4D.
Yeah, the point is 2D and 3D I didn't get to because the theories themselves are somewhat ill-defined, right? 2D, for example, the moduli space, there's
Right.
a moduli space, right? Because there are infrared divergences.
Right.
So 4D somehow is in the boundary. It has infrared divergences, but it is somewhat under control. In 3D, for example, if you try to create a massive state, that it
You
produces a conical,
Conical, yeah.
a conical defect, right? So it changes asymptotics.
So, but somehow you're saying that 3D and below should be excluded then from the space of vacua. They are not real vacua or something?
Well, yeah, I'm not saying that with confidence, but I didn't do it because of this annoyance that I don't know what to do with the fact that the asymptotics gets changed every time I put a party. But maybe there is a way to get around it, but it's just that it's much easier to start with 4D and higher.
I see. So supposing I was in 3D only, and I took your point of view that vacuum. So are you saying that one should not think of vacua of 3D, or that they are not naturally in the same space as vacua of higher D?
So you can think of vacua in 3D, except that once you have a massive particle, it produces this conical defect, and then it looks like the vacua changes. So you cannot. So particle spectrum in 3D. Is a somewhat ill-defined object concept because the vacuum itself changes, right? Asymptotics change.
Yeah, but somehow we are accepting that, right? By saying that supposing I make a particle in some region B, which is inside A, and there the asymptotics appear to change, but actually, I mean, can I not think of it in the same spirit as being a vacuum of realizing a theory in a subregion which looks like a different theory?
But see, here what I discussed, the asymptotics will never change, right? We said the asymptotics is A, right? And whatever we create in the interior, the asymptotics you are not going to change.
But there'll be some sort of local asymptotics in the interior, right? When you create something in the interior, the fields will go to some boundary value inside your B region, and then they will come back to the values in the A region through that domain wall or whatever.
Yeah, except that in this case, there is not even in the black hole example, it's a completely smooth transition, right? There is not even a domain wall.
Yeah. Okay.
It's a smooth transition.
Right.
But it is true that it looks like in the interior there is a asymptotics, because otherwise you cannot do experimental arbitrary large accuracy.
Yeah.
But that asymptotics is not really at infinity, right?
No, of course.
It looks asymptotics, but it's really a finite volume.
That's right. But
I'm asking, you really change the asymptotics, right?
I see. So there's no reinterpretation. I'm just guessing that maybe in 3D there's a reinterpretation of creating a particle in a way that actually changes the asymptotics only inside a finite region. And
I don't know of this.
I mean, one example could be starting with a 3D situation where there's already some number of particles. Then as we move them around, then different regions appear to have different asymptotics, right?
Yeah, that may be possible. That is certainly possible, right? So then the point is you start with a certain number of particles already, and then you can move things around to create black holes.
Right.
Yeah, that is in principle possible.
Okay.
Then you are not changing asymptotics. Yeah.
Okay.
More questions?
Are T4, T3 connected by this construction? Like not general.
Yeah. So T4, type 2 and K3 is connected to heterotic on T4, right? But type 2 and T4, of course, is different from type 2 and K3. Right? So I started with T6. In fact, it's related to this earlier question, because from T6 you can go to higher dimension, right? You can decompactify easily using this. And I didn't do T7 or larger because my understanding of what you mean by keeping the asymptotics fixed is limited, right? Because that as soon as you add a particle, you get your asymptotics change, right? So when you are saying you are going to create states using black holes, right? Then that means you are changing your asymptotics, right? So is that a state of the theory or not? In 4D, there is no doubt that if you create a black hole in the middle, in the interior, right, asymptotics remains flat. That's certainly a state in the original theory, right? And you are using that to create these large regions where you have this other type, other moduli. So in that sense, in 4D, you can be more conservative, right? Nevertheless, you have a lot of freedom in going to higher dimensions.
Sorry, Ashok, I was trying to do it in my head. I was not able to, but I was trying to do this calculation for the anti-D3 brane in ADS to check whether the Schwarzschild radius grows faster. Is that something that is easy to do on the borders? That's what I'm doing.
Okay. I mean, I know how to. I mean, I convince myself by looking at the flat space.
Okay.
Right.
Yeah.
In flat space, once you have an anti-D3 brane, right, then you have become non-extremable.
Yes.
Right? So clearly, there is a horizon that encloses the whole thing.
Yes.
Right? So now you could try to take a limit, right? So you encounter horizon before you even encounter the branes.
And but what about, sorry, this I haven't yet understood. Suppose I separate, there's a modulus for your initial starting position.
Yes.
That is arbitrary.
Yes.
And I can't make that large enough so that it's not within the.
I think even if you make it large enough, the horizon will be outside, right? Because okay, one way to see this is the following. That if suppose you are in point at a patch, right? Then it's really like a one-dimensional problem.
Yes.
In the z direction.
Yes.
Right? In one dimension, if you add a mass, right, you already change the asymptotics, right?
Yes.
Because the gravitational field grows linearly.
Yes.
Right, and I think this is something like that. That adding adding a D3 brane doesn't change it because mass and charge somehow conspire.
Yes.
Right, but having an anti-D3 is like adding a mass in a one-dimensional system.
Now, why is it one dimension? Why is it one? What about the R6 around it? Say we were doing D3 brane.
So I'm using Poincare. In Poincare patch.
You're in ADS, you're saying.
Okay. Yeah, in ADS. Yeah.
In ADS. Okay, I get you. You're saying the S5 is compacted.
Yeah, S5 is compact, exactly.
Okay. Yeah, that much.
Yeah, but one can try to probably work it out and see what happens, right?
Yeah, so probably some obvious. Okay.
I think it will be related to this one-dimensional issue, I think, because it will be. I mean, if you do the Poincare patch, then it's a one-dimensional differential equation.
Even here, it would be one dimension. I was thinking of a spherical.
Yeah, even for spherical, yeah, because the flux. I mean, there is a limited size anyway, right?
Exactly.
You are thinking there is no horizon?
I was just wondering. I mean, it's clearly as this anti-D3 brane grows large, its energy goes to infinity. The question is, does it go to infinity faster or slower than a black hole of the same radius?
Yeah.
It probably should be obvious. Right?
Yeah, one shouldn't be able to resolve even ADS asymptotics probably with this anti-D3 brane.
Right. Yeah, you're saying it goes to infinity so fast.
Yeah.
That it's.
Yeah, and that's a reflection of the fact that in the original flat space viewpoint, right, you have more charge and more mass than charge.
But at any finite radius, of course, it preserves that as ADS asymptotic.
Yeah.
I was wondering now a black hole that is all. I'm saying the same thing. That a black hole that is also that big, also, if you made it bigger, would violate ADS asymptotics.
Yeah.
The question is which way does it? Which is faster?
Okay. Yeah, this is something one should be able to check.
Very easily.
Yeah, exactly. Right. And if it's the other way, right? Then it will say that from SUN you can measure SUN plus 1.
But it may also be that this doesn't work. I think you're right, but it could also be that this doesn't work, and yet this just collapses very fast.
That's also possible. Yeah.
I think it, as you said, because of the speed of light,
Yeah.
it will collapse very fast.
Yeah.
So even if you can create a finite energy, you want to make it live long enough.
Yeah.
It could be that is the barrier.
Yeah.
But what if you want to do experiments that last only a little time? Then you should be able to.
But this will be this will be time of order. If it's the field theory is of radius 1, this will be time of order 1. So now, if you want to do some experiment involving, let's say, an operator of dimension 2, that's not long enough. So, I mean, there's no parametric separation.
Any more questions? If not, let's thank Ashoke for